Today we continue talking about 3.1. We're going to finish 3.1 and then talk about section 3.2 as well. The last part of 3.1 deals with different ways of essentially solving quadratic equations. Equations that in general form would look like ax squared plus bx. We can say plus c equals a number. Usually we have it equal to 0 when we're solving. And there are multiple ways to solve these quadratic equations. First of which is by completing the square. Completing the square, the general form of completing the square is given to you here, kind of like the steps to completing the square in terms of the a, b, and c. And then here's an example. We can follow along with this one here so that we can see the process laid out step by step. So if we start with an ax squared plus bx plus c, first thing we want to do is we want to isolate this. We want to factor out the a so that we don't have to deal with that within this parenthesis. Because what we're going to do is we're going to complete the square, as it says, in this parenthesis here. But we don't want a number in front of the x squared. So we factor out the 2. When we factor out the 2 from the 2x squared, we just have x squared left. When we factor out the 2 from the negative 12, we're going to have negative 6 left. And then we still have the plus 5 at the end. So this step is kind of a weird step because we usually don't talk about taking this trinomial and just focusing on the first 2 and factoring something out of it. And even then, if we looked at these two last time when we did our factoring practice, we talked about, what do these two have in common? And we're going to factor that out. This is not what we're doing here. Because if we were factoring out whatever they had in common, we would also take out an x, right? Because they both have x's in their expression. So we're not taking out everything they have in common. All we're doing is we're making it so that this term in the front doesn't have the 2 in front of it, the number in front of it. We just want an x squared term by itself. So in the process, whether this 2 can be factored out of the 12 or not is insignificant. We're always going to factor out this 2. Even if this was like an 11, let's say, we're still going to factor out a 2. Now that's going to create some fractions and some weird expressions for us, but that's okay because that's what completing the square is going to involve. Sometimes you're going to have to deal with fractions, and hopefully we have an example of that in here. It doesn't look like we do, but I'll maybe write an example where we do have fractions so you can see that it's okay to do that with fractions. And then once we have it in this form, we are absolutely just focused on what's happening in this parenthesis. We want to complete the square in that parenthesis so that this parenthesis, notice how the 2 and the plus 5 are going to remain all the way down to here, right? The 2 and the plus 5 are still there. But we're going to complete the square so that that parenthesis becomes a parenthesis, a binomial squared, right? So how we do that is we have a very systematic approach for doing that. What we do is we find b over 2a just in this parenthesis. So in this parenthesis, we have x squared plus bx. That's essentially the form that we have in the parenthesis, right? And there's no number in front of the x squared, so I don't have to write an a there. I know it's always going to be 1 once I get to that parenthesis. And I have a plus bx. Now that b, in that case, is a minus 6. So what we're going to do is we're going to figure out what b over 2a is using that b. So negative 6 over sorry. The 6 is the. I don't want to write this here. Get rid of that if you wrote that down. Why would we do this way? Okay. It is a bit different than how you would find this online. But from the original equation, we have a, b, and c, where a is 2, b is negative 12, and c is 5. So from there, we're doing b over 2a, not from this parenthesis. Usually, once we get to this parenthesis, we could just focus on b over 2, and then square that, and then add that into the parenthesis. But if we want to use this idea of b over 2a, we're going to have to use these as the a, b, and c. So this b over a is the 12 over 2, so negative 12 divided by 2, which if we simplify this, that's 1/2 of negative 6, which is negative 3. And then we're going to square the value from step 2. So we're going to square this final value that we got here, negative 3. We're going to square that. That gives us positive 9. Next step is to add this value to complete the square in this parenthesis. And then since we added something in the parenthesis, we need to subtract something outside the parenthesis. So since we're going to add 9 here to complete the square, that's the value we got from step 3. Technically, if we add something in here, we want to subtract the same amount outside the parenthesis. Now, it looks like I added 9 here, but we actually didn't add 9 to this whole expression, right? By adding a 9 inside this parenthesis, what we've actually added is 2 times 9, because remember this 2 is going to distribute into this parenthesis, right? So by adding a 9 in this parenthesis, we've actually added 18, because the 2 times 9 is 18. So we have to subtract 18 outside the parenthesis. Or we should probably write it as 2 times 9 so that you know where that came from. 2 times 9 is what needs to be subtracted outside because we added 2 times 9 in the parenthesis. And finally, this parenthesis, now that we've added the 9, is what we call a perfect square. So this is a perfect square. And the square that it is always x minus, remember the number that we squared to put inside the parenthesis? It's that number. So we're going to have a x minus 3 here. So this number and this number are always going to be the same. So if you keep track of this number that you got before you squared it in step 2, that's the number that you'll need when you write your parenthesis as a x minus something or x plus something squared. And then the minus 18 out here. And then all we do in the last step is to combine this negative 18 with this positive 5. So we have x minus 3 squared and then a minus 13 out here when we combine those. So that does seem like a lot of work, but it's because we're following this with showing like every single step is why this seems like a really long-winded process. It's really not that long, and it doesn't really have to be broken apart into this many steps. Although this is what's happening in the details, usually when we're doing these problems, there's only really 1, 2. There's only really 3 steps here that are significant. So let me do an example with one of these guys. Let me do an example. Let me do the next 3.1.8 part B, so that I can show you the kind of the shortened version of what we just talked about. First step is going to be to factor out the number in front of the t squared, because we don't want to have that there. So we're going to factor out the 3. And what's left here is the t squared plus 4t plus blank. I'm going to write a plus blank there because we know we're going to add something in the parenthesis, and then we can write a minus blank outside the parenthesis. In order to counteract whatever we add in here, we're going to have to subtract out here. So you can go straight from the first, from the given expression to this kind of expression in essentially one step. And this is all the way down here. So we're going to go straight to this, and we're going to do a bit of side work to figure out what goes in the blank, and then we'll almost be done with this example. So within this parenthesis here, we're trying to complete the square. What's going to go into this blank here is, we'll do side work here. We're going to take the middle term, which is the 4t. We're going to take its coefficient, and we're going to divide by 2. 4 divided by 2 squared. And that's what's going to go into the blank in the parenthesis. Okay, so you take the middle term, you take the coefficient of the middle term, you divide by 2, and then you square. And that gives us 2 squared, which is equal to 4. Right, 4 divided by 2 is 2. Squaring that gives us 4. So what we're going to add into the parenthesis is 4. Once I add that 4, this thing in the parenthesis is now a perfect square. I've completed the square, but we can't just add something to the expression without also subtracting it outside. What did we actually add to this whole expression? It looks like I added 4, but remember that 4 is being multiplied by something, so we didn't actually add 4, right? What did we add for? What did we add to the expression?
12.
12, good. And that's going to be, I'll write 3 times 4 out here so you remember where the 12 came from. But what we actually did is we added 12, which means we need to subtract 12 outside the parenthesis. So as far as the steps go, that's the main step of completing the square. Up here in the detailed, like, step-by-step process, this was broken down into like 1, 2, 3, 4 steps, right? We just did the first 4 steps basically at once by just factoring out the 3, putting the plus blank and the minus blank immediately, and then taking this middle coefficient, dividing by 2 and squaring it, and then adding that inside and subtracting it outside the parenthesis. So second step is going to be to rewrite this parenthesis as a binomial squared. So the 3 is going to stay. I want this to become something squared because we know that's what completing the square means. And then outside the parenthesis, we have a minus 12 and a plus 2. So we'll combine those on the last step to write our answer. But in this parenthesis, what we're going to have is essentially this factored out into 2 parentheses. But the 2 parentheses are going to end up being the same thing, so we can combine them into a single parenthesis squared. And this is always going to be the first variable, which is t, plus or minus whatever this value was. in the when we did the divided by 2 before we squared it. So I'm gonna actually highlight that. That value inside of the parenthesis is what goes here. So 4 divided by 2 is 2, so this must be a plus 2. I'm going to draw an arrow from there to there so you know where that 2 came from. It's always going to be what's in that parenthesis. And then finally we can write our answer here in the third step. We have 3 t plus 2 squared minus 10. Right, that's the process. I know the first thing we did had like 17 steps, but it's really not that complicated. It's factoring out the number because we don't want the a to be involved in the situation, and then putting a plus blank minus blank, figuring out what goes in the blank by taking the middle coefficient and dividing by 2 and squaring it, and then putting that into your blank, and then subtracting it outside, but remember that the 3 distributes into the parenthesis before you subtract it outside. And then after that we write it in as a perfect square, so we take whatever this was in the parenthesis before we squared it, and then that is your number that goes after your variable. Any questions on this example that I just did? Okay, why do we learn completing the square? Well, it's essentially to solve quadratic equations. It's one way of solving quadratic equations. And instead of doing one of the other examples, instead of doing this one, I'm going to let's stay on this page. We'll just draw a line here and essentially add an exercise here saying solve h of t equals 0. So if we had a question where we were actually trying to figure out when this original expression h of t, when this would equal 0, we actually can use completing the square to kind of efficiently solve this. So what does it mean for h of t to equal 0? Well, h of t is 3t squared plus 12t plus 2 equal to 0. That's how we would start the problem, or that's what would be given to us to solve. And then completing the square, we completely work on the left side. We complete the square at this, right? So we're going to say from here we can complete the square to get to the final expression that we had, 3 times t plus 2 squared minus 10, and we would still be equal to 0. So we do the process that we did up here in the 3 steps right here. I'm not going to redo the steps because we just did that for that function. I kind of want to show you how to proceed after this. So let's take this expression. I'm actually going to do this. We'll say from here to here we complete the square. And then from here we can actually solve this using all of the tools that we already have on how to solve equations. So we want to get t by itself, right? Which means we need to get rid of everything around it. So the first thing we need to get rid of is the 10. So we add 10 to both sides. Oh, not 0. Positive 10. And then we need to divide both sides by 3. So t plus 2 squared equals 10 over 3. And it is a fraction, and it is kind of gross, but it is what it is. So we just continue working with it. How do we get rid of the square on the parenthesis?
Take the square root.
Take the square root. What do we need to remember when we take the square root of both sides?
Is it the plus or minus?
Yes. It's the plus or minus. We have to put a plus or minus in front of either one of the sides. It makes more sense to do it on the side with the numbers, as we talk about numbers being positive or negative. So I'm going to put the plus or minus in front of the square root of 10 over 3. And that leads us to the square root gets rid of the square. So t plus 2 equals plus or minus square root of 10 over 3. And then the last thing we need to do is subtract 2 from both sides. And I'm going to write this as t equals a negative 2, because I'm going to have the plus or minus in between two things. You don't necessarily have to put this in order, but it's nice to have plus or minus as an operation rather than like a leading coefficient. So that's what t would equal, so that this original expression is equal to 0, right? So if I take these numbers, which there are two of them, right? There's the negative 2 plus square root of 10 thirds and the negative 2 minus square root of 10 thirds. If I took either of those and I plugged it into my t's in my original expression, I would get 0. So we just solved this quadratic equation by completing the square. Other than completing the square, we can also solve these quadratic equations by factoring, which we know how to do at this point. Hopefully, we know how to factor. We know how to factor using a common factor. We know how to factor out the greatest common factor, and then we also know how to do like the AC method for trinomials in order to factor into two parentheses, right? That's what we did last time. So how can we use that? Well, we use this thing called the zero product property, which is going to be very important to solving by factoring. Zero product property says that if you have two things, A and B, just they could be numbers. They're going to be expressions in our case, but representing numbers. If you have two numbers multiply together and they give you 0, then that means that one of those two things or both has to be 0, right? So this idea that you can't get 0 unless you're multiplying by 0 is what we're going to use here. So a question says solve the equation 0 equals negative 16t squared plus 160t by factoring, determine the time when the firework will reach the ground. So there was a firework apparently given by this equation. A firework's height off the ground is given by the negative 16t squared plus 160t. So we're going to solve this by factoring. So we'll say, okay, 0 equals negative 16t squared plus 160t. Factoring just means factor this expression on the right side. We're no longer completing the square. We're just factoring like we did last time. So we look at what these two have in common first. What do they have in common? What can we factor out?
Negative 16t.
Yeah, negative 16t. And you can do positive 16t as well. But let's take a negative out so that the first term isn't negative in this parenthesis. When I factor out a negative 16t, what I have left is t plus 10, because 160, when I take out 16 from 160, when I divide that out, I get 10 left. And these are being multiplied together, right? We have a negative 16t times a t plus 10, which is essentially the a and the b from the zero product property. So we can say that since there are two things multiplied together, technically there are three things multiplied together, right? The negative 16 is multiplied by the t, and then that's multiplied by t plus 10. But this negative 16 is never going to equal 0. So we can kind of just ignore that one, or we can include it in the next step. We can say that either negative 16t equals 0 or t plus 10 equals 0. Right, so we take the two things that are multiplied together, we set each one of them equal to 0, and then we solve each one. They should be pretty simple to solve after this point. We can divide by negative 16 on the first one. Divide by negative 16. Well, I guess both sides. Divide by negative 16, divide by negative 16. And then on the other one, we're going to subtract 10 from both sides. Oh, I'm sorry. What did I do wrong?
The t plus 10.
What's wrong with it?
It should be t minus 10.
Why should it be t minus 10?
Because you factor out the negative.
Yeah, so when we factor out a negative from the positive 160, we're going to end up with a negative 10 in here. So that when this distributes back in, we get back to a positive 160t. Okay, so let's fix that real quick. This should be a t minus 10. And then to solve that, we're going to add 10 to both sides. So we get t equals 0 or t equals 10. So in the context of the equation, if we look back up here, remember this was the height of a firework, and t was time in seconds after it's launched off the ground. So this is essentially solving the time when the firework is on the ground. So it makes sense that we have two answers because the firework starts on the ground at time 0. So this is representing before launch, right? At time equals 0, before the firework is launched, the firework should be on the ground. That makes sense. And then this time equals 10 is telling me that after 10 seconds, firework returns to the ground. Right, because we got t equals 10. So this idea of factoring to solve is different than the completing the square. So we have completing the square to solve, we have factoring to solve, and then we have one more way of solving, which is on the next page, which this is just showing you how we arrived at the quadratic formula. But essentially, what you need to be concerned with is knowing the quadratic formula in that box and knowing how to use it if you have a quadratic equation given to you where it's equal to 0. It does have to be equal to 0 for this equation to work. So your a, b, and c have to be in this form: ax squared plus bx plus c equals 0. And then you can just plug in your a, b, and c into this formula to find what x is going to equal. So we can do the same problem with the firework. to figure out when the firework reaches the ground, but we want to use the quadratic formula now. So let's identify the a and the b and the c, and then we'll plug it into our quadratic formula. So 0 equals negative 16t squared plus 160t. What's my a?
Negative 16.
Good, that's the a. What's the b?
160.
Good, what's the c?
0.
0, because technically there's nothing after this, but technically we could just put a plus 0 and that'll be our c. I don't recommend writing the plus 0 when you're doing this every time, but just know that if a term is missing, it's just 0, right? If the b term is missing, then b is 0. We are going to just plug things into the quadratic formula now. Quadratic formula says x equals, but that's because it's ax squared plus bx plus c. In this problem, we have t's instead of x's, so we're going to say t equals when we start our quadratic formula. And this is going to be one big fraction. Negative b will be negative 160 plus or minus a long square root. B squared will be 160 squared minus 4 times a, which is negative 16, times c, which is 0. So we have to extend this square root, extend this fraction. So 4 times a times c, and then over 2 times a, which is negative 16. Right, so quadratic formula is kind of a kill-all solution where it will solve any quadratic equation, but numbers can be pretty big and gross if you jump straight into this. What we did last example with the factoring by solving was a little bit simpler, where we could just like work by hand. And we can work this one out by hand as well. It's just we have to be a little bit careful. This negative 4 times negative 16 times 0 is just equal to 0, right? Because we're multiplying by 0, so all of that will become 0, which means we have negative 160 plus or minus square root of 160 squared, whatever that is. I don't really want to calculate it right now. But 2 times 16 is 32, so we have a negative 32 on the bottom here. We notice that the square root and the square can cancel each other out, right? Because we just have a square inside of a square root. So those can cancel out. Essentially, we have a negative 160 plus or minus 160 divided by negative 32. And now we're going to split into two equations. Let me actually make myself a little room here by putting this here. We're going to take this and we're going to split into two equations, or two expressions. First one is t equals negative 160 plus 160 divided by negative 32, or t equals negative 160 minus 160 divided by negative 32, right? Because we have the plus or minus there, which means we can split into the two forms, the plus and the minus, separately. So this is how we split using the plus or minus. And then here, negative 60 plus 160 is 0, so we get t equals 0 in that case, because 0 divided by negative 32 is also 0. Or, when we simplify this one, this gives us t equals 10. So we get to the same two answers. Negative 160 minus 160 is negative 320, and dividing by negative 32 gives us 10. So the same answers Again, this is before launch. And this is 10 seconds after launch, as far as the firework is concerned. Are there any questions? Okay. Determine the maximum or minimum. We complete the square. So to determine maximum or minimum value of a quadratic, we have to write it in something called vertex form. And vertex form is essentially y equals a x minus h squared plus k. That's what vertex form is. And you'll notice this form looks very, very similar to something we did today. We ended up with something that looks like this when we completed the square. When we completed the square in the very first page, when we completed the square with this h of t, we ended up with something that looks very similar to that. We have the a, the h, and the k. Right? So if you take this expression and you complete the square and you put it into this form, so it looks like that, then h comma k is the vertex. And the vertex of a quadratic function is its highest or lowest point, right? Remember the quadratic functions are in the shape of a parabola. So this point that is the lowest point or the highest point, if it's an upside down parabola, that's what we call the vertex. So if you want to find the maximum minimum values, you're going to want to find the vertex. If you want to find the vertex, you're going to want to put it into vertex form. If you want to put it into vertex form, you're going to have to complete the square. Okay, so complete the square to put it into vertex form, and then from there you can pull the vertex, and that'll tell you the highest or lowest point of the quadratic. Okay, and then you guys can work through this one in your groups. As far as 3.2 is concerned, 3.2 is about power functions and direct variation, inverse variation. Direct variation, inverse variation is not super difficult to comprehend. Whenever you see varies directly, you're going to want to use this type of equation, y equals some number times x to a power. So in this example here, it says y varies directly with the cube of x, which means we take that sentence, just this right here in the box, and that translates to y equals ax to the third. Okay, because it says cube of x. Okay, so that box, using this idea of direct variation, automatically gets us to this direct variation equation. And then we can use some initial conditions, like if y is equal to 25, when x is equal to 2, we can take those two things and plug them in to x and y. And then the only thing we won't have there is the a, right? We can use this. We can use these. Use these to find a. And then finally you get to what the question is asking, which the question is saying to find y when x is equal to 6. Once you know what a is, you have a relationship between x and y. So then you can just plug in the x to get the y at the end. I'll say plug this in at the end. So what does that look like? That looks like you start with this. You start with the y equals ax cubed. We plug in the 25 and the 2. So 25 equals a times 2 cubed. Right, so 25 equals 2 cubed is 8. So we get 8a here. 8 times 8, or 8 times a. And then we divide both sides by 8 to figure out what a is. So we use the 25 and the 2 to find a, which in this case is 25 over 8. That allows us to write an equation. Y equals, now that we know what a is, we can rewrite this, but now we know what the a is. A is always going to be a constant. So from here, we combine these two things and we get y equals 25 over 8 x cubed. And now that we found a and we've put it back into our equation, we can actually answer the question of what is y when x is equal to 6. So this is the end where we plug in 6 for x. So y equals 25 over 8 times 6 cubed. And simplifying that, we have 25 over 8 times, I don't know, 6 times 6 times 6 to make our life a little bit easier. We can simplify one of these 6's with the 8. This is a 3 and this is a 4. We can simplify the other 6 with the 4. This is a 3, this is a 2. We can simplify the other 6 with the 2. This is a 3, this is a 1. So we get 3 times 3 times 3 times 25, which, what is that, 27 times 25, which is 675. Right, so that's how we do direct variation problems. There's another example here that you can do, you guys can do. Are there any questions on any of those steps that I just did? Okay. Inverse variation is very, very similar as far as the steps are concerned, but the starting equation is going to be a fraction instead. So we're going to start with y equals a over x to the p. So if it says y varies inversely with the cube of x, then you would start with y equals a over x cubed, and follow the same steps to answer the question. All right, so just the starting equation is different if you have an inverse variation. You guys can do those problems. Power functions. You should know the properties of exponents. If you don't, make sure you look these up and fill this table out if the video didn't already give you these properties, and then you can use the properties here in this example to determine if each one is a power function. A power function has to be in this form: f of x equals ax to the n. There cannot be anything added or subtracted or otherwise. The exponent and the coefficient have to be real numbers. But having the exponent be any real number gets us into kind of different types of power functions, right? So there's a big difference between like x or y equals x to the second power, which is a whole number and a positive whole number, and y equals x to the negative 2, right? As soon as we allow exponents to be negative, we know that this becomes 1 over x squared, right? We enter the realm of reciprocal functions, so 1 over x squared. And if we allow exponents to be anything, we also have things like y equals x to the 1/2, which brings us into the world of square root functions, right? Or radical functions. If we had 1/3, it would be a cube root, and so on. So we have kind of three different worlds that we go into with allowing this exponent to be anything. And those three different worlds are, well, I guess 4 different worlds, are shown in this end behavior table. The three different ones that you should focus on, or the ones that I just talked about, are the positive powers, which are these ones over here, the even power, odd power. So these two together are the positive powers, positive whole powers. These two here are negative whole powers. And the last two here are what do we want to call these? I guess we'll say rational power. I don't want to say rational. We'll call them we'll just call them fraction powers, because they're going to look like fractions. We're concerned with what happens as x goes to infinity, what happens to the function. So in each case, you have two different, so for example, if we focus on this one here, which we know what a parabola is, if we focus on this parabola box here, where x is to some even power, so this works with x squared, x to the 4th, x to the 6th, they will always follow this kind of shape. Now x to the 4th may do like another twist in the middle where it turns multiple times, but we're more focused on what's happening on the endpoints of the graph, which this and this is describing the end behavior of the graph. So if your coefficient is positive, meaning the number in front of the x squared, so like y equals ax squared, if that a is positive, we've talked about this before, we know that the parabola opens upwards, right? And if the coefficient is negative, we know that the parabola opens downwards. So that's what we're looking at in this box here specifically. And we can kind of do that idea for any function. So if we have like y equals x to the negative 2 power, if there's a positive number in front of it as a, then this is what the general shape of the function looks like. If we have a negative number in front of the x to the negative 2, this is what the general shape of the function will look like. So you need to be able to use this table to identify end behavior of functions given to you. So let me pick a random one here to talk about. Let's talk about this one here, the negative 3x to the 7th. So the a here is negative 3. And my exponent is whole, or positive and whole. Positive, whole, and odd. So we're going to go to our table, and we're going to find the box where the exponent is positive, whole, and odd. And then we're going to look at the box where the coefficient a is negative. So if I go back here, positive whole powers are over here in these two sections. And then I have an odd power, which means I'm in this box here, right? And my a was negative, which if I look at the top, that's the second column here. So we're in this box. So our graph is going to look something like that. And this is going to be our end behavior that we're going to write as our answer. So we're going to say, we're going to write it a little bit differently. I don't really care for the limit notation in this class. We may get to limits later on, but right now we haven't really talked about limits. So let's just say, let's just write it as x goes to infinity, g of x goes to, we're in this box here, so as x goes to infinity, g of x is going to go to negative infinity. And as x goes to negative infinity, which means if we go left on the graph, if we go towards the left, then I can see from the graph itself and from the equation given below that g of x is going to go to positive infinity. Or I guess, yeah, positive infinity. We don't really write the positive if it's just positive infinity. We can just write infinity. But that's the end behavior that we're describing. Meaning, if we go right along this graph, we're going down forever. If we go left along this graph, then we're going up forever. Right? So you're going to do that for those examples that ask for end behavior. Any questions on that?